Hiya. Okay, so just a little brief recap. We've looked at ocean colour theory on Wednesday, a little bit about what ocean colour is, how light goes into the ocean, it's absorbed, scattered, then reflected back, and its spectral variations in that light that dictates our ocean colour. A little bit about the history of the ocean colour, so going back to how colour was used for navigation purposes. A little bit about the theory of optical properties in the water, how pure water is blue, but when we add our various optical constituents to that water, our phytoplankton, our sedum, our backscattering, we modify the colour of the water from blues to our greens, to our browns, to our yellows, and so on and so forth. We also looked at how we measure ocean colour in situ, some of those very old techniques we talked about, the Secchi disc, lowering this disc into the water and measuring the distance at which it disappears from sight. Our Forel-Ullet colour scale, these old colour scales used to measure the colour. Our more modern techniques now using radometers above ships to measure reflected light, using radometers in the water to measure the colour coming out the ocean, the apparent optical properties of light, and also our inherent optical properties, our absorption and backscattering meters on CTDs, on-the-way ships, and so on and so forth. And then about satellite remote sensing and how we need to correct for the atmosphere in order to get accurate data on the colour of the ocean. And then yesterday we talked about the marine carbon cycle, how we can retrieve properties related to the marine carbon cycle, related to the pools of carbon in the ocean, particular organic carbon, phytoplankton carbon, our particular inorganic carbon, coccolithophores and things like that, and how we can use this ocean colour data to try to constrain the things we can't see from space, the pools we can't see, our DIC, dissolved inorganic carbon, dissolved organic carbon. And so today we're going to be talking about ocean colour and climate. Okay, so just to put it in a bit of context, this is a very similar slide to what I started with yesterday with the carbon cycle. The point being that we have been pumping the atmosphere with CO2 since the start of the Industrial Revolution, way back somewhere here. And the atmospheric growth in CO2 concentrations is estimated to be about 4.7 gigatons of carbon per year. I actually went on to the Hawaiian station, Mauna Loa, in Hawaii, to look at the latest CO2 readings from their station. And June 2008, we reached 410 parts per million. And if you remember, it was only a few years ago, there was a lot of media coverage about us first bridging the 400 parts per million range. So CO2 concentrations at this station just over the past few years have continued to increase. And of course, this is a big worry for us because we know that we fill the atmosphere with CO2. It's going to affect our climate. And this was a nice illustration from a paper by Victor and Kennel showing graphically how our planet is suffering from this increase in CO2 and how we have to monitor the vital signals of our planet in order to understand how it's changing in response to this increase in CO2 emissions. So in 1992, the Global Climate Observing System, GCOS, identified 50 essential climatic variables to support the work of the Intergovernmental Expert Group, the United Nations Framework Convention on Climate Change, and the Intergovernmental Panel on Climate Change. So an ECV, or essential climatic variable, is defined as a physical, chemical, or biological variable or group of variables that critically contributes to the characterization of the Earth's climate. So in 2010, the European Space Agency launched their Climate Change Initiative, and they essentially identified some of these essential climatic variables which we can monitor from space, all shown here, and that you'll be learning about over the next 2 weeks. Now, in the oceans, there's 4 CCIs. There's sea ice, sea surface temperature, ocean colour, and sea level. Of course, this talk's going to focus very much on the ocean colour part. But just to go over very briefly the other components, this is some data from the sea surface temperature CCI. So the goal with this project is really to produce a stable error, with all these CCI projects, is to produce a stable error-characterized climate quality data set that we can use to monitor these vital signals of our planet. And so this is the sea surface temperature record, and as we can see, since the early 90s, there's been a steady, well not steady, there's been an increase in sea surface temperature. There are periods where the sea surface temperature stabilized for a bit, but there's a lot of evidence, or we know now, that a lot of heat was being taken up by the deep ocean during this period. If we looked at ocean heat content, for instance, there would be much more of a steady increase during these periods. We can see over the more recently, 2015, 2016, we had a very large El Nino El Nino event, according to the El Nino Southern Oscillation, and we reached the warmest temperatures we've recorded during this time series. Sea level, you've already heard some nice lectures earlier this week about the sea level, but again, according to the sea level CCI, our sea levels have steadily been increasing during the time series for which the sea level CCI has produced a data set for. And this is down to various components that make up the sea level, which you've been learning about earlier this week, that related to the hydrological cycle, thermal expansions of the oceans, and so on and so forth. And there's the sea ice CCI, which has been monitoring sea ice and has been also showing changes in sea ice at the poles. So ocean colour. Why is ocean colour an essential climatic variable? Well, the ocean colour is our only window into the marine ecosystem from space. It gives us information about phytoplankton, and phytoplankton are an essential component of the Earth system. For example, they've contributed to between 50 to 85% of oxygen in our atmosphere. They are critically linked to many planetary biogeochemical cycles. We learned yesterday about the marine carbon cycle and how fundamental they are in the marine carbon cycle. But also other biogeochemical cycles as well, related to climatically relevant compounds and elements. Phytoplankton are also at the base of the food web, so they sustain practically the majority of marine organisms in the ocean. With some exceptions, for instance, I don't know if you watch Blue Planet, but probably doesn't categorise for the bird-eating fish that we saw on Blue Planet. But it does, in terms of fisheries, there has been clear examples where the colour of the ocean, or the phytoplankton in the ocean derived from ocean colour, the productivity of the ocean derived by ocean colour is very well correlated with fishery yields. Okay. Oh yeah, and finally, as I mentioned yesterday, phytoplankton, the cycles of phytoplankton are relatively short, within days, so they have the capability of responding very quickly to changes in the physical and chemical environment. Okay, so this talk, I'm going to go over the data sets needed to monitor climate variability from ocean colour. So I'm really going to focus in on the Ocean Colour Climate Change Initiative here and the process that this project has undergone in order to produce climate quality data sets for ocean colour. I'm then going to talk about some of the responses of the marine ecosystem to a changing climate. So what would we expect to happen if our climate changes to the marine ecosystem, and how can we carefully monitor those responses? And then I'm going to finish off by talking about some examples of climate variability observed during the ocean colour record. Okay, so when GCOS put together these essential climatic variables, they come with a series of requirements, and these are the latest requirements, I believe, in 2016. There were some early ones the CCI project worked with in 2011. And essentially, these are the goals we need to meet in order to ensure that our ocean colour data set is of climate quality. And these requirements are listed for all the ECVs that GCOS look at. And there's this document here that's available to download off the internet if you want to have a look at any of this. So in terms of ocean colour, the goal is to, well, in terms of any ECV, it's to create a consistent error-characterised time series of global satellite ECV products for climate research and modelling. Now, for ocean colour, our requirements are a horizontal resolution of 4 kilometres. For 2 different products, we look at water-leaving radiance or remote sensing reflectance. The remote sensing reflectance is just the water-leaving radiance divided by the downwelling irradiance. So they're essentially very similar things, just to avoid any confusion, because I've talked a lot about reflectance earlier. And the second is the chlorophyll concentration, which we talked about yesterday. So we want a horizontal resolution of products of 4 kilometres. We don't need to worry about the vertical resolution because they're 2D fields, though, as we discussed, the signal coming from the ocean colour varies with so the depth of that signal could be deep in the oligotrophic environments where there's little material, or it could be shallower in productive environments. And we want a temporal resolution of daily for water-leaving radiance and weekly for chlorophyll. I'm not so sure why these are different. It's not clear to me why these are different. We want an accuracy of water-leaving radiance of 5% in blue to green wave bands. Now, this was, in the 2011 requirements, 5% across the whole spectrum. But as we learnt on Wednesday, pure water absorbs very strongly at these red wavelengths, which means the signal coming from the ocean colour in the red part of the spectrum is very, very low. And we would be, there's no way we're going to meet this requirement of 5% in the red. So in the 2016 GCOS requirements, this changed to just looking at blue to green wavelengths. We want an accuracy in chlorophyll of about 30%. Now, these accuracy requirements, we need to show that we meet these. But firstly, it's not entirely clear where these requirements have come from. There is actually, as of last year, there is the opportunity for the public or for anyone who's interested to comment on these requirements, and GCOS take this into consideration when they create their next requirements list. So it's an iterative process, these requirements. But certainly the 30%, my understanding is the 30% in chlorophyll comes because we derive chlorophyll from water-leaving radiance, and if we haven't got water-leaving radiance within a 5% accuracy, we're not going to retrieve chlorophyll within 30% accuracy. So in terms of stability, so this is percent per decade. These are the requirements. We need a stable stability in our water-leaving radiance of 0.5% and our chlorophyll of 3% per decade. So they're the goals. Now, this is a flow diagram of how the OCCCI data processing chain works. At the moment, there are in the latest processing, 4 ocean colour sensors that are used in this. There was an earlier ocean colour sensor I talked about very briefly, I think, in the Wednesday presentation called CZCS. This was a proof of concept ocean colour sensor from mid-1970s to mid-1980s. I'll talk about that a little bit later on, actually, but it wasn't included in this processing chain, partly because it was a proof of concept, so the quality of ocean colour observations in this sensor doesn't meet the requirements of these more modern sensors, and also there wasn't any overlap between the CZCS sensor and some of these ocean colour sensors, which is very important if we want to correct and ensure our ocean colour record stable. So the sensors that go into this OCCCI processing chain are the CWIF sensor, which operated from 1997 to 2010. The MERIS sensor on board Envisat, which operated from 2002 to 2012. The MODIS Aqua sensor, so the MODIS sensor on the Aqua platform for 2002 to present. Recently, in the last few reprocessings, they've been including VIIRS as well, so this is the NASA NOAA platform, and there's a lot of ongoing work working to incorporate the Sentinel sensors, which will happen in the near future. So we have all these different ocean color sensors. The first thing we need to, well, we have these data sets. The first thing we need to consider is obviously the radiometric and spectral calibration. In order to use these data sets, we need to understand the uncertainties in these components and make sure these sensors are radiometrically and spectrally calibrated as best we can, which the space agencies are already doing in this case. So assuming that they're very stable and spectrally stable, we need to apply our atmospheric correction. So the atmosphere being the dominant signal in our ocean color. And so to do that, we do a series of round-robin comparisons. And this is quite an open process. So we test a number of different atmospheric correction algorithms on all these sensors. And we determine which one is the best, both in terms of performance, but also in consideration of that we want to have a climate quality data set. So once we've atmospherically corrected our data, we need to first do some band shifting, because all these ocean color satellites have a slightly different set of bands. And what we do is we shift the bands in these sensors to a common band set. In the last few versions of CCI, that has been the band set used by CWIFs. It might change in the future. I'll talk a little bit about how that's done in a minute. And then we need to bias correct these data sets. So we need to ensure that they're all consistent. And so we do that by matching observations near coincident observations from these satellite sensors and correcting them to a common platform, which in the last few versions has been the CWIF sensor. And then we merge the data. So once we merge the data, we have our remote sensing reflectance, or our water-leaving radiance. We then need to, which is, if we go back, one of our essential climatic variables. But we also want chlorophyll concentration and other products as well that OCCCI produce, the inherent optical properties in the ocean and the diffuse attenuation coefficient. So to do that, we need some in-water algorithms. And we go through the same process we do with the atmospheric correction. We test a series of in-water algorithms, and we determine which algorithm performs the best in the context of a quantitative performance and a qualitative performance. And we have our unified multi-sensor products. We need to quantify per pixel uncertainty. It's essential that we have quantify the uncertainty in these observations. And to do that, we actually use independent in situ observations. I discussed this a little bit yesterday and on Wednesday, this fuzzy logic membership, how we do that. I'll mention it again in a minute. And so once we've done that, we have our products. We also have this step here where we quality control. We analyze this data as rigorously as we can. We make it available to the community. And if necessary, we go back through this loop. And actually, we've gone through this loop. I think they're close to producing version 4 now. So they've gone through this 4 times. And these products are then provided or made openly available, so modelers, oceanographic scientists, Earth observation scientists, and in particular climate scientists can access them at a suite of temporal scales, daily, weekly, monthly, annual, so on and so forth. Okay, so a bit about the intercomparison, so whether we're talking about the atmospheric correction or the in-water. We have 2 considerations with this. Firstly, we want the best performing algorithms, right? So we need to determine how well the algorithm performs and rank it. But also, we need to consider some more qualitative things. How well does this algorithm suit the requirements of OCCCI? So, for instance, do we want to use an algorithm that ties chlorophyll with CDOM, if we know that in a future ocean, CDOM and chlorophyll might decouple, as an example? And then we rank these algorithms. There's some additional considerations about sensor-specific performance, comparisons with time series and so forth, and make our algorithm selection. Now, this is very much an iterative loop. So this is done every time we go around this again and again, partly because that allows us to incorporate new emerging algorithms that might be performing better than, or may be performing better and may be more suitable for our needs than the algorithms we've used in the past. Okay, so a little bit about the band shifting. So to do that, we actually use an inherent optical property model. So what we do is we take the reflectance data from these different platforms, we invert it to get to our inherent optical properties, and then we band shift on the inherent optical property level and then go back up to reflectance. So it's all documented, a lot of work done by Frederick Mellon of JRC does this work. And then once we've done that, we have our common band set. We essentially match these observations on a common grid, concurrent observations on a common grid, and then look at the relationships between remote sensing reflectance, say at 443 nanometers from one sensor and the other, and what models we can use best to make those bias corrections. And then we use an IOP model when we start also for our products. So this is just an example of a day of Meris radiance data, MODIS, Aqua, and CWIS. So this, I haven't included VIRS here. This is from one of the earlier CCI processings. And you can get an idea of what a daily image looks like from these sensors, going through this process of band shift and bias correction and merging, and these kind of products we get out at the end. So for the uncertainties, we have compiled an enormous data set of chlorophyll observations around the global. Well, I say this is enormous. This is enormous for ocean color. If you do sea surface temperature, then this is minuscule compared to the sea surface temperature observations. But for chlorophyll observations, we're really pleased with this. And then we match these observations in time and space with our satellite observations from CCI. And we use this optical classifier, optical water type classifier. So basically what it does is you have a series of optical water types here, going from one very clear waters to our very bright turbid waters. And how this works is it looks at a satellite pixel and it essentially derives the fractional contribution of all these water types to that pixel. So if it's out in the middle of the ocean, it's going to be, 80% one, 10% two, so on and so forth. If it's at the coast, it'll probably be 12 or something, 50% 12, 20%, and you sort of get the idea. And so with these matchups, we bin the data into dominant optical water types and compute the errors in each of those optical water types. We can then reweigh those errors and produce pixel-by-pixel errors at a global scale, which is an example here. So here we have our dominant optical water type, boom, 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 boom. In reality, each pixel has a membership, and we weigh that membership according to, we weigh the errors according to the membership in order to produce a map like this. Okay, and so this is just some examples from the first version of the CCI project that I got from Schuber. And what we can show here is that the relative error in our remote sensing reflectance in blue at the top here and in green at the bottom here, the majority of the ocean, according to our errors, they're lower than this 5%. So we seem to be meeting the GCOS requirements. It is, I didn't mention actually in the first slide, but it's something we need to be a bit careful with the word accuracy. And there's been a lot of debate going on over the last sort of decade about this, what accuracy actually is, what statistics to use for accuracy. And so just bear that in mind, that you could use one statistic for accuracy that might meet these requirements, or use another statistic for accuracy that might not. So just bear that in mind. But in our case, the statistic we used met the requirements, and that wasn't fortuitous. We were as objective as we could be in this process. Okay, the other great thing about merged ocean color products is you can significantly improve the spatial coverage in your data. And so this is an example from, I skipped a slide then. No, okay, it's the next one. from the Red Sea. So here we've got the Red Sea here, Gulf of Aden, and going out into the Indian Ocean. And this is a climatology of July from the MODIS sensor, from the CWIF sensor, and CZCS sensor. So climatology, it's all the observations over a 10-year period, roughly, of ocean colour. And you can see there's huge gaps. Whereas our product, or the product coming out of the OCCCI project, fills this gap. This isn't a climatology, this is just a single month in July. So we observed better spatial coverage with this product. And part of the reason this was for, actually, was for using a polymer atmospheric correction on MERIS. So this is the daily coverage in percent from CDAS, MODIS, and MERIS going into version 1 of the CCI product. And the atmospheric correction algorithm, which came out best in our round robin, was polymer. And it had it has an ability to work well in sun-glint regions, for example, and significantly improve the coverage. So this, you get an idea of how much daily coverage we have with our merged product. You can immediately see in this image atmospheric features, for instance, regions of the ocean which are very cloudy, regions of the ocean which aren't very cloudy, which is why we get very good coverage of ocean colour. And also with our CCI product, we were also improving the coverage over other merged products, in this case glob colour for this example. And this again was partly due to using the polymer algorithm on MERIS, which we were getting many more retrievals. Okay. So that's a bit about the Ocean Colour Climate Change Initiative project. So now I'm going to walk through what are some potential responses of the marine ecosystem to a changing climate. And I'm going to start with the total amount of phytoplankton as indexed by chlorophyll concentration, though as we discussed yesterday, we could be using an index of carbon, but I'm going to talk mainly about chlorophyll in this, might change. So the total biomass of phytoplankton might change with changing climate. So just to put this into a bit of context, there was a paper published in 2010 in Nature, which reported a global decline of phytoplankton over the last century. Now, this wasn't from satellite observations, obviously, because we don't have 100 years of satellite observations. This was from in situ observations. And if I take you back to the first lecture we did on Wednesday, I talked a bit about the Secchi disk. The majority of observations pre about 1950 were from Secchi disk observations. So what the authors did is they converted the Secchi disk readings into an estimate of chlorophyll. They then merged that data set with existing observations of chlorophyll and then looked at trends over the global ocean. Now, this paper received a lot of criticism at the time. There were 3, I think, rebuttals or brief communications arising, as they call it, arguing whether blending data sets does blending chlorophyll data bias temporal trends. I think this paper, actually, I would have to read it again, but was related to the amount of data, spatial coverage, and so forth. And then there was also some work showing that other data sets of phytoplankton, this being the continuous plankton recorder, which is a device operated by the NBA now, was a SAFOS, but they've merged with the NBA. That's an institute in the UK in Plymouth. They operate this continuous plankton recorder. They've been doing it since about the 1920s. This is this huge steel device that's towed on ships of opportunity, and it essentially filters phytoplankton as it moves, and that phytoplankton's then stored and then brought back to the lab. There's data sets going back to the 1920s on this. And in their data sets, which was just in a specific region in the North Atlantic, they saw quite the opposite. So there was a lot of controversy over this. Now, since the authors have published another 2 papers, and they've took all these criticisms into account, reanalyzed the data sets, and reproduced 2 nice papers on this. And they argue in their latest paper in 2014 that actually the majority of conclusions drawn in this first paper hold. But there's still a lot of work being done in this area at the moment, and a lot of controversy still. Now, what was quite nice, what I quite liked about this this paper is with these nature papers, there's often a sort of a preempt. Someone comes in and writes a little bit about the paper. And so this was written by a couple of scientists, one at NASA, another in the US, who both work with a lot of satellite observations, and they argue in this paper that the analysis of voice document the historical record. Looking into the future, however, satellite measurements will be the main source of data assessing change in pelagic ecosystems. So moving forward, it will be the satellites that we rely on in order to monitor phytoplankton. Okay, so jumping back to what I mentioned a bit earlier about this old proof of concept sensor. So this is the period that the CZCS sensor operated from the mid-1970s to around the mid-1980s. There was then a 10-year gap before all our other ocean colour sensors started to come aboard. And there has been work looking at what the chlorophyll concentrations were during these two periods. Now, one of the biggest difficulty with this is bridging these two data sets. I mean, we know that the CWIF sensor is a higher quality, better characterized sensor than CZCS was, which was just proof of concept. However, we don't know, it's very difficult to compare these two without some independent data set. So what Watson Gregg did in 2002 is he used actually in situ observations to bridge these two types of data sets and looked at chlorophyll from CWIFs during 3-year period, 97 to 2000, and CZCS 97 to 1986. So we have our CWIFs at the top, CZCS here for 2 different seasons, and then looked at differences between the two. And he concluded that chlorophyll, he and his co-authors concluded that chlorophyll had declined over this period. So there was a reduction in chlorophyll. You can see it's generally lower in these top 2 images than these, as reflected in the bottom one. Another approach by David Antoine, what he and his co-authors did is they went a slightly different route and instead tried to focus on the processing method, so the atmospheric correction algorithms. They used a consistent coupled ocean-atmosphere correction algorithm that could be run on both sensors, and also verified it against in situ observations during the periods of the 2 sensors. And then looked at differences. So this is the log ratio of chlorophyll and CWIS by chlorophyll and CZCS, and concluded that actually over the global ocean, chlorophyll has been increasing. So here are 2 contradictory conclusions based on comparing CWIFs and CZCS. Now, there was a second paper following David Antoine's paper by Elodine Martinez. She was actually another postdoc of the European Space Agency. And she used the data sets that were produced in the Antoine paper to look at relationships with biology and physics. And I'll mention her a little bit later on in this talk. But here she demonstrates quite nicely that these changes, spatial changes in chlorophyll between these 2 periods, are related to physical changes in the environment, which is what we'd expect because phytoplankton respond to the environment. Another example, this is just in the northeast Atlantic here, was by a colleague of mine, Dionysios Raitsos. And what he did quite nicely, I thought, was he used the PCI, the CPR record I talked about earlier, this thing that's towed on ships of opportunity, in order to bridge these 2 different data sets over this period. And he concluded in the Northeast Atlantic, he and his co-authors, that the chlorophyll concentrations have increased during this period, CZCS to CWIFs. Okay, but moving forward now, we have a continuous time series of satellite observations from the late 90s all the way through to present. And looking forward, for instance, with the start of the Sentinel time series, this time series should continue long into the future, touch wood. So these data sets are continuous now. We don't need to look at time periods which different time periods. Touch wood won't have gaps in our observations. Okay, so initial work looking at trends in some CWIF's products are shown here. This is a paper by Greg and Rousseau. I probably mispronounced this second name, so I apologise for that. In 2014, and they looked at a series, sort of the literature review of different methods to look at trends in chlorophyll over the CWIS periods, different data sets, slightly different resolutions in their case here. This is their effort. And using different techniques, so linear regression of a chlorophyll time series, deseasonalizing that time series and looking at a linear regression, or using a model-based approach where you partition that time series into a seasonal component and a long-term trend and a residual, as in Van Tropez and Milan. And these are just some examples of trends reported by these authors over these periods. So here's this from Greg in 2005 over the 1998 to 2003 period. These two are the same periods here, 1997 to 2007, one by Henson, one by Van Tropez and Milan. More recently, a paper by David Siegel looking at the CWIF's trend in chlorophyll, and CWIS modus here, which was the work by Greg et al. And this is what we're seeing. This was a paper published by Fred Mellon in 2017 in the Remote Sensitive Environment Special Issue. So this is what we're currently seeing based on our Ocean Colour Climate Change Initiative product. So this is an 18-year trend. And you can see by looking at this that there are various parts of the ocean that or seem over this period to have reduced their chlorophyll, Indian Ocean, some of the equatorial Pacific, parts of the Atlantic, but there's also large parts of our oceans where the chlorophyll concentrations have been increasing over this period. But just to make the point here, what Fred did nicely in his paper is he also looked at trends at different points during this time series. So this is an example of a trend from the same product from January 1998 to December 2007, and one from August 2002 to 2011. And you can see quite contrasting features in these trend maps. For example, in the equatorial Pacific here, there's almost a completely different trend. Now, part of the reason being is, this was a nice slide lent to me by Marie-Fanny Racole. We need to define what we mean by climate variability and climate change. So climate variability is defined as short-term in terms of years, rises and falls about the mean state of the climate, whereas climate change is a longer-term, multi-decadal to century-long data set that can look at persistent rises and falls in either the mean state of the climate or its variability for an extended period. So we're clearly down in here at the moment with these comparisons. We're observing short-term climate variability related to things like the El Niño, La Niña Southern Oscillation, as I'll discuss in a bit. This was a nice paper that came out in 2010 by Stephanie Henson, who's now at the NOC in Southampton. And what she and her co-authors did here is they used some climate models that were forced with different IPCC scenarios, I believe, or it might have been a single IPCC scenario over the period, I think, from 2000 to 2100, and then used the model output to try to determine the length of time series we need in our ocean chlorophyll or productivity products in order to detect anthropogenically induced climate change. And from her analysis, she and her co-authors concluded that we need a time series of 40 years in length to distinguish a global warming trend from natural variability. Now, naturally, these times will vary spatially, depending on where you are in the ocean. So we're approaching 20 years now, and hopefully with the Sentinel time series of data, we will reach this 40-year period. Okay, so some implications for satellite chlorophyll algorithms to consider. Firstly, in order to detect chlorophyll or expect how chlorophyll may change in the future, the retrievals of properties of the ecosystem should be independent of each other. We talked about a bit yesterday slightly, but also on Wednesday, about how these case 1, case 2 conditions, how in case 2 conditions, chlorophyll does not covary in a predictable way with CDOM and backscattering. Now, we don't know in a future ocean whether the relationships between chlorophyll and these other optically significant properties will be different to how they are now. In that case, we need an algorithm that will retrieve chlorophyll independently of variations in these other properties. We also need uncertainties in our observations, which is what the CCI have tried to produce. And we want an ocean colour record with minimal gaps. And there's some nice work by Stephanie Henson and colleagues who have looked at the effects of gaps in our ocean colour record and how that impacts our ability to detect these long-term trends. And our algorithms should be robust in a changing environment. And this leads me on to the next point here. So, for example, if the phytoplankton community structure changes, it should not interfere with the performance of our algorithm in estimating chlorophyll. And this is an example of that, actually. This is a paper by Hurturu in 2014. And he used some data from these AMT transects. I talked a little bit about that on Wednesday, about going to sea and making these measurements. And he looked at the trends over a very short-term period. It was, I think, only a 7-year period. In situ chlorophyll, also looked at some satellite CWIS data. And then he looked at the trends in phytoplankton community composition, derived from high-performance liquid chromatography, so other pigments in the phytoplankton, and showed that in some cases, for instance, in the tropical Atlantic here, there was no significant change in chlorophyll in situ, but we saw significant shifts in community structure. Also, there's been a series of papers that I've been involved with, and also one nice one by Ben Ward in 2015. Actually, that shouldn't be an et al. He was the single author of this paper. Here we have on the y-axis here the fractional contribution to total chlorophyll of very small phytoplankton, so our picoplankton. And we show here that this fractional contribution as a function of total chlorophyll varies with environmental conditions, being light in the mixed layer or being temperature, as in these two examples here. So what does that mean if we want to look at phytoplankton, how phytoplankton community structure changes with climate? It means we need to focus on these detection-based algorithms for estimating phytoplankton community structure. So we need algorithms that allow the retrievals of spectral variations in phytoplankton optical properties. We need these algorithms that detect the signatures of the community, not rely on empirical relationships or semi-empirical relationships between the community structure and chlorophyll, like I discussed a little bit yesterday. Okay, other substances might change. I've made this point already, but this is just to hammer it home that the detrital component, for instance, the way bacteria maybe in 100 years, how CDOM, how some of those carbon processes we talked about yesterday, how POC is converted into DOC through excretion, how that might change and impact our CDOM concentrations. We don't know. So we want to retrieve we want an algorithm that will retrieve our ocean color properties independent of each other. And we're also interested in CDOM. We're also interested in detrital matter. So if we want to look at how climate changes these other properties, we don't want them to be affected by covariations with chlorophyll. One thing I haven't talked about too much over the last few days is phytoplankton phenology. So phytoplankton phenology is basically the seasonal timing of the phytoplankton bloom. So in order to look at the phytoplankton phenology, we need to construct a time series at any given location of phytoplankton over the period of a year, say here. So this is just an example from the Northwest Atlantic. And then what we do to quantify metrics of phytoplankton phenology is we look at things like the initiation of the phytoplankton bloom, how long the phytoplankton bloom lasts, and duration, and its peak timing and its amplitude. So all of these indices may change from year to year. Now, what Trevor Platt and Shubha Sathyendranath and others have done a lot of work on phytoplankton phenology. And what they've shown, certainly by Trevor's Platt paper in Nature in 2003, is that interannual variations in the timing of a phytoplankton bloom impacts the survival of larval fish. So here we have an example of an index of larval survival as a function of anomalies in the timing of the spring bloom. So basically, when the spring bloom was later than it was on average, we see a higher survival rate. When it's earlier than average, we see a lower survival rate. So phytoplankton phenology has a profound impact on these higher trophic levels that are feeding on the phytoplankton, as shown here. So this is proposed by Cushing, called the mismatch hypothesis. And it basically describes this mechanism why mechanism favouring early blooms of phytoplankton. So, for instance, this mismatch being when the fish larvae spawn and when the phytoplankton bloom is critical. If they spawn and there's no algae to eat, then they're going to die. If they spawn and there's lots of algae around, they're going to survive. And Marie-Fanny Racole, who was another actual postdoc of the European Space Agency, she did her postdoc on this work. She looked at looked at long-term changes in these properties. And in this case, she demonstrated that the duration is actually, changes in duration are actually closely linked to changes in total chlorophyll. Okay, so implications for phenology algorithms. We want an ocean colour record with minimal gaps, as we discussed earlier, for other properties. But we also want an ocean colour record with maximal temporal frequency. This is an example from our CCI product in the Red Sea. And so this is the percent coverage of weeks here, practically 100% in OCCCI data, compared to our single sensor products. So what Marie argues here is that we should be using products like OCCCI to look at long-term phenology. Okay, so finally I'm going to go through some examples of climate variability observed in the ocean colour record. So what we often use when we look at climate variability is climate indices. So a definition of a climate indices, or a climate index, is a simple diagnostic quality that is used to characterize an aspect of the geophysical system, such as a circulation pattern. There are a variety of methods to do this, from single points to regional averages, and using statistics like we heard a bit about earlier, empirical orthogonal functions and things like that to define this climate index. And this needs to be over a given period. So it's recommended that about 30 years of data are required for one of these climate indices by the World Meteorological Organization. Some common examples of these indices include the El Niño Southern Oscillation, the Indian Ocean Dipole, the North Atlantic Oscillation, the Pacific Decadal Oscillation, the Southern Annular Mode, and the Southern Oscillation Index. Okay, so I'm jumping back now to Elodie Martinez's paper in Science where she was comparing the CZCS data with the CWIFS period, with CWIFS data from a similar period in CWIFS. So this is a 20-year comparison. And what she showed quite nicely in this paper is that the principal components of the time series were quite closely related in different regions to these climate indices. So in the Pacific, for instance, the first principal component was related to the Pacific Decadal Oscillation. In the Indian Ocean, the second principal component was also related to the Pacific Decadal Oscillation. And in the Atlantic, there was a significant relationship with the AMO. Atlantic Meridional Oscillation. There were some nice papers that came out early 2000 looking at El Nino Southern Oscillation and how that impacts ocean productivity. This nice paper in Science looked at the big ENSO event we had in 97, 98, 99, showing how the oceans respond to these changes in climate, particularly in the Pacific Ocean, but also globally. And another paper in 2006 which showed how the net primary production correlates very well with the multivariate ENSO index. And I showed this plot yesterday and earlier as well. This is an example from our CCI record. 18 years of data overlaid onto the same index, and you can see how well it tracks variations in ENSO. Marie-Fanny Racco, as part of her ESA postdocs, also been looking at different types of El Nino. So you have this Eastern Pacific El Nino and the Central Pacific El Nino, and this has different impacts on chlorophyll and primary productivity, and also the phenology parameters we talked about, growth duration in this case. I've done some work with others looking at the Indian Ocean dipole. So this is an index in the Indian Ocean, which is essentially a difference in the sea surface temperature anomaly between a region in the east and a region in the west. And this is related to a coupled atmospheric ocean phenomenon, and how that affects the chlorophyll concentration, but also the phytoplankton community composition. There's ongoing work at the poles. A lot of work now looking at the colour of the ocean at the poles. This is an example of a nice paper in 2014 in GRL that looked at the phenology, how the phenology of phytoplankton is changing in the Arctic. So what you typically have observed in the past is phytoplankton bloom in the spring, then they bloom again in the autumn. So it's a sort of two-bloom situation. But the further you go north, that merges into a single bloom. And that's been known for a long time. But in a changing Arctic Ocean, what they're finding now is that the single bloom phenology is actually, you're seeing spring and fall blooms in the Arctic. And that's going to have large implications for the organisms that feed on these phytoplankton. Also, this is an example from our OCCCI data set in the Southern Ocean. So this is the trend in chlorophyll from, it's actually slightly longer, from 1997 to 2016. This was produced by a colleague at PML. And what we're seeing generally in the Southern Ocean is increases in chlorophyll concentration. And this could be related to a number of factors. For instance, as water melts off Antarctica, it's often rich in nutrients, which can, particularly micronutrients in the Southern Ocean, such as iron, in which the phytoplankton are iron limited. But also, as there's less sea ice, or as the sea ice changes with climate, it's also exposing more light into the ocean, which is igniting phytoplankton blooms. So I think there's going to be some interesting stories coming out of this. Okay, so I'm just going to wrap up now. I've gone over the data sets needed to monitor ocean colour climate variability. So this OCCCI product, all the steps that we've gone through in order to ensure that we have a climate quality data set. And then also some of these potential responses to the marine ecosystem to a future ocean. Will the total amount of phytoplankton change? Will the community structure change? Will these other substances in the water change? And will the phenology change? And then finished off by looking at some examples of climate variability observed in the ocean colour record to date. So again, I'll just direct you to some further reading. There's a load of references, actually, Marie kindly gave to me that I've just dumped in there. And also, she has a very nice paper in Frontiers in Marine Science, which looks at the implications of changes in ENSO around the globe. And I just want to finish off by saying I'm going to have to leave fairly shortly. So it's been really nice meeting you, all of you, over the last few days, and I really enjoyed some of the conversations I've had with you. And if you have any further questions about any of this or any of the conversations we've had, please don't hesitate to send me an email. Okay. Yeah.
Okay, any questions now? Yep.
I just have a very general question in the context of rising CO2 levels.
Mm-hmm.
For the phytoplankton, would that also act as a kind of a fertilizer?
Yeah.
And then on the other hand, when you think about the pH levels in the ocean, what's the balance between those? Do the pH levels have a negative effect?
Yeah. So there's evidence on land-based systems, from my understanding, that when you increase the CO2 concentrations, you're actually starting to fuel more photosynthesis, essentially. Now, whether that's been shown in the ocean, I'm not sure, so I can't really answer that question. But there is the potential. Now, in terms of ocean acidification, you're quite right. Rising CO2 levels, assuming the ocean continues to absorb these CO2 concentrations at the rates it has been, then the ocean will become more acidic, and that has already been shown to have some quite profound implications on marine organisms and potentially how they photosynthesize. So yeah, it's a very good question. I've probably fobbed you off a little bit. I don't really know the answer to. Sorry.
Any other questions? I just have a quick question about anthropogenic activity, such as the discharge of nutrients from fertilizers, from industrial activity into the oceans. Is it possible to measure any impact that may have on the global phytoplankton?
Potentially, yeah. So quite right, actually. I focused mainly in this talk on the open ocean. I haven't really gone into the details of the coastal ocean. So one of the phenomena you just mentioned is eutrophication. So as we change our agricultural practices around the coastline, more and more nutrients are flowing out into the coastal ocean, and that's causing eutrophication, very large blooms of phytoplankton, harmful algal blooms and things like that. So yeah, I just want to underline that point. I've kind of focused mainly on the open ocean. But yeah, I mean, there is work looking at, for instance, how much colour-dissolved organic matter coming off the ocean, which we can see from space, how far that goes out into the ocean. So yeah, I think there's definitely potential to do that work.
Is it a major contribution or not
so? In what sense?
I mean, does it have a huge impact on the global phytoplankton and
okay, so would eutrophication, yeah, I don't know, to be honest. I mean, the coastal, for instance, I know the upwelling regions around the ocean are responsible for large amounts of the productivity. So, yeah, it's probably a good question to try to attack, but I haven't heard or seen anyone look at that, how significant that is with respect to the open ocean.
Okay, thanks a lot.